Simulation and optimization in the design phase focus on testing and improving the design virtually before actual implementation. Simulation involves creating digital or mathematical models of the product, process, or system to predict how it will behave under various conditions, helping identify potential issues, performance bottlenecks, or failure points without physical trials. Optimization uses these simulation results to fine-tune design parameters, processes, or workflows to achieve the best possible performance, cost efficiency, reliability, and quality. Together, simulation and optimization allow teams to validate designs, explore alternative scenarios, reduce risks, save time and costs, and ensure that the final product or process meets customer requirements and operates efficiently in real-world conditions. Monte Carlo simulation is a statistical technique that uses random sampling to predict how a design or process will behave under variability and uncertainty. In simple terms, it runs the design thousands of times with different possible inputs to see the range of outcomes, reflecting real-world conditions where raw materials, machine speeds, and human performance can vary. It is used to estimate best case, worst case, and most likely scenarios, calculate the probability of failure, and assess the likelihood of meeting critical to quality CTQ requirements, helping teams make informed, risk-aware design decisions. Monte Carlo simulation works in a few simple steps. First, identify the uncertain inputs, or X's, that can vary in the system. Next, assign probability distributions to these inputs such as normal, uniform, or triangular distributions. Then, run thousands of trials or iterations using random samples from these distributions. Finally, observe the resulting output Y distribution to understand performance variability, identify risks, and uncover opportunities for improvement. Manufacturing, a milling machine designed to produce parts of 20 mm plus or minus 0.2 mm can experience variability from tool wear, machine vibration, temperature changes, and operator handling. Using Monte Carlo simulation, thousands of trials are run with these varying inputs to determine the percentage of parts likely to fall outside the tolerance, how often the machine will require calibration, and the overall risk of failure over time. This helps engineers anticipate issues and optimize the design or process before production. BPO process Monte Carlo simulation can be used to predict average handle time AHT when agent skills, customer issue complexity, and call volumes vary. By running thousands of simulated scenarios, it can show, for instance, that under the current process design, there is an 18% risk of out exceeding 300 seconds. This insight helps managers identify bottlenecks, adjust staffing, or redesign workflows to reduce delays and improve service performance. System modeling is the creation of a mathematical or digital representation of how an entire system operates, allowing teams to analyze and understand its behavior before actual implementation. It helps examine process flows, material movement, queues and waiting times, workload balancing, resource utilization, and potential bottlenecks. There are different types of system models: discrete event models, which simulate queues, waiting, and resource usage; continuous models, which simulate flows, temperature, speed, or pressure; and hybrid models, which combine elements of both. By building these models, engineers and managers can test scenarios, optimize performance, and make informed decisions without disrupting real-world operations. System modeling is useful because it allows testing and analyzing a design safely without interrupting operations, incurring costs, or exposing the system to real-world risks. For example, in manufacturing, modeling an assembly line can simulate the number of workstations, cycle times, buffer sizes, worker allocation, and conveyor or robot interactions. Running such a model helps identify bottlenecks, optimize workflow, balance workloads, and ensure the line operates efficiently before implementing any physical changes. In a service or BPO environment, system modeling can simulate a customer support queue by considering factors such as call arrival rates, number of agents, breaks and shift patterns, and ticket priorities. This allows managers to calculate SLA achievement, determine the required headcount, and estimate queue lengths during peak periods, helping optimize staffing and ensure timely, efficient customer support. Robust design is an approach that ensures a product or process performs consistently even when uncontrollable factors, called noise factors, vary. These noise factors can include temperature, humidity, voltage fluctuations, operator differences, or material variations. The goal of robust design is to make the system insensitive to these variations, reduce output variability, improve reliability, and minimize the cost of poor quality, resulting in a more stable and dependable product or process. Taguchi's robust design methodology is popular because it focuses on maximizing performance while minimizing the impact of variability. In this approach, the signal represents what you want the system to achieve, while noise represents uncontrollable factors that cause variation. Control factors are the design parameters you can adjust, and orthogonal arrays are special matrices used to plan experiments efficiently. The signal-to-noise SA ratio measures performance relative to variability, with a higher ratio indicating better robustness. Taguchi methods require fewer experiments than full factorial designs, provide deep insight into sources of variation, and help build robust, high-quality designs that perform reliably under real-world conditions. In manufacturing, designing a welding machine involves control factors like current, voltage, and feed speed, while noise factors include material thickness and operator variation. Using the Taguchi method helps identify the combination of control settings that minimizes defect variation and ensures consistent weld quality. In service or IT, designing a chatbot response system involves control factors such as algorithm version and timeout settings, with noise factors like network speed and server load. Taguchi analysis helps determine the settings that deliver consistent response times even under varying conditions, improving reliability and user experience. Design optimization is the process of refining a product or process after simulation and Taguchi experiments to find the best combination of design parameters. The goal is to maximize performance, minimize cost, reduce variation, and ensure all critical to quality CTQ requirements are met. Various methods are used for optimization, including design of experiments to systematically test factors, regression modeling to quantify relationships, response surface methodology RSM for exploring parameter effects, linear and nonlinear optimization techniques, genetic algorithms for complex designs, and multi-objective optimization when balancing competing goals. This ensures the final design is efficient, reliable, and aligned with customer needs. The optimization process begins by clearly identifying CTQ performance requirements so the design goals are well defined. Next, a predictive model is built, typically expressed as y equals fx, to understand how output performance depends on key input parameters. Experiments or simulations are then run to generate data, after which optimization algorithms are used to determine the best combination of x's that meet objectives such as higher performance, lower cost, and reduced variation. Finally, the optimized solution is validated through real-life testing or additional simulations to confirm results. For example, in plastic molding, parameters like injection pressure, cooling time, and mold temperature are optimized to increase strength, reduce scrap, and shorten cycle time, with software identifying the ideal sweet spot. In a service or BPO context, ticket routing can be optimized by adjusting skill-based rules, load balancing, and priority logic to reduce SLA breaches, resulting in improved SLA performance from 89% to 96% without increasing headcount. Monte Carlo simulation helps understand how uncertainty affects performance by using random sampling to predict risks and outcomes, such as variations in average handle time in ABPO environment. System modeling creates a digital representation of a process to study flow, queues, and resource usage, making it easier to identify bottlenecks before real implementation. Taguchi Robust Design focuses on making designs insensitive to noise factors, reducing variation and ensuring consistent performance as seen in setting optimal welding machine parameters. Optimization then brings everything together by identifying the best combination of design parameters to maximize performance while minimizing cost, such as optimizing mold temperature and pressure in manufacturing.